Welcome to our course Metallocene and Metal-carbene based organometallic catalysts for advanced polyolefin catalysts. So far we have discussed the prospect of Metallocene based catalysts for olefin polymerization. We have learned that how these emerging catalysts have really revolutionized the polyolefin industries, and then we have tried to compare with the Ziegler-Natta catalysts the advantage over the Ziegler-Natta catalysts, and we have seen that the stereoselectivity is much better for the Metallocene based catalysts, and also the activities, especially to get the high molecular weight polymers. You have learned that CGC based like titanium based catalysts are much more superior, and it is very easy to understand the stereoselectivity associated with the prochiral monomers, and you can basically control to make a particular stereoselective polymers. We can make the stereo block polymers by selecting your catalyst. So you can use the catalyst as a toolbox, and according to your desire, you can select the catalysts. And then we have also discussed the recent advancement in non-metallocene or called post-metallocene based catalysts, and we have seen that catalysts like Buchert catalysts, which are palladium based catalysts, are very much efficient for like non-polar molecules, not only the non-polar, also for the polar olefinic monomers. So we can have a very diverse library of the catalysts in this scenario, and you can basically make a whatever you want. You can make the different type of homopolymers, block copolymers, or a specially designed polyolefin based homopolymers like that. Today we will discuss mostly the synthesis of the LLDPE. As we have already learned that LLDPE, that is the linear low density polyethylene, is a category of the polyethylene, and you know that polyethylenes are one of the heavily used plastics in our daily life, and for bulk and for various sophisticated purpose, as example like medicines or various domains like cosmetics, like packaging industries, and etc. So today we will discuss the polymerization strategy for industrial preparation of the LLDPE. Okay, so let's try to learn today. So what are the concepts? The concepts we will learn the olefin polymerations. Okay, and we will learn here that oligomerization is also important, and how we will take the advantage of the oligomerization of say ethylene and try to use it in LLDPE preparation. And then we will see what are the strategies followed by industries to make the LLDPE polyethylene. And we learn here what are the cell higher olefin process. So it's basically this is called SHOP process, HOP. It's basically to make the oligomers of the ethylene, so to make like a hexene, butene, pentene, heptene, like that, so that it is used for alpha copolymerization and to make the LLDPE in industries. Okay, and obviously we'll learn how this catalyst operates. So we'll have to have a depth knowledge of the mechanism and the catalytic process, so that we can understand the process associated with this one, and how this bond breaking and bond making are happening in the polymerization reactor. Okay, so the key points we will learn here: the ethylene oligomerization, that is very important, because unless we do it, we cannot really make the LLDPE. Okay, and we'll see how we can do the LLDPE synthesis with the combination of the ethylene oligomerization and the polymerizations. Both are important here. Okay, so this we have already learned in previous classes, that polyethylene, we know that one of the heavily used polymers in various domains. Okay, I'm not going to repeat again. Various type of polyethylenes are possible, like low density polyethylene. Okay, the high density polyethylene, we know that the low density polyethylenes are synthesized by free radical polymerizations, free radical pathway. Okay, and the high density polyethylene, generally we do Ziegler-Natta catalyst. I'm just write Zn. Okay, Zn catalyst system. Medium density polyethylene, also Ziegler-Natta catalyst, and this is the one of the very interesting and very useful materials, that is the low density polyethylene. Okay, that is the linear low density polyethylene. So you can here you see that this is basically in between the LDPE and the MDPE. So the branching associated, you see there is a smaller branching, shorter branching, and less number of branching. So and here you will see the LDPE, that is a low density polyethylene, is a more number of branching, longer branching. There is no control in the branching of the from the main polyethylene moiety. Okay, and why it is important, this is very special. Okay, and due to the small number of short chain, here you will see this is the small number of short chains. Okay, these the short, and numbers are smaller than the LDPE. Okay, and so this is actually, that's why it is low crystalline polymers. Okay, and this is basically the more number of shorter and smaller branches than the high density polyethylene. Okay, if you compare with this one, and that's why it is a low crystalline polyethylene, and due to that there are several interesting properties. As example, like here, higher elasticity. Okay, the higher toughness. Okay, higher flexibility, because this is low crystalline, and easy transference. See, because it is a low density polyethylene, excellent molding ability. This is important. So that's why we can excellent molding ability, and that's why we can make a different type of materials by the LDPE. We can shape it according to our need, and as it is, you see that it is flexible and easy transparency. So this actually, the LLDPE polyethylene are heavily used in packaging industries and to make the flexible materials, even for the medical industries. Okay, and pharmaceutical industries. And this we discussed in our previous class, that this LLDPE is a global market is used. Okay, you will be very surprised that by 2026 the global market size is almost like $50,000 million US dollars. Okay, million US dollar. That is the global market size. So you can understand that how this LLDPE, okay, apart from the other polyethylene polymers, how these are important in industries. Okay, because it is a very high global market. Okay, so now it is, we are very much familiar that why LLDP is very special, okay, for various applications in many domains. Now, how to synthesize the LLDP? That is our aim, that how we synthesize LLDP, how we can control to have a short chain but limited short chain, okay, not like a free radical polymers. The polymers obtained from the free radical polymerizations of the alkenes or ethylenes. Okay, so what we have to do? I write down the strategy, and then we'll discuss that how we can do in real life. Okay, so what we have to do? We have to, so this ethylene, we know that this is, if you do the polymerizations, we will get like, okay, okay, so this is polyethylene, okay, and this is the ethylene monomer. Okay, so this is the, you can use the catalyst or you can use the any other free radical initiator. Okay, so now how I'll make the LLDP? Okay, so what we have to do, basically we have to do through the copolymerization. Okay, copolymerization. So LLDP is not really the homopolymerization product. It's a copolymerization of what? Of ethylene plus the small number of short chain alpha olefins. Okay, so small number of short chain alpha olefin. Okay, so something like that. Okay, so R should be here the smaller alkyl group, and this is the ethylene. Now you see here it is written the small number. That means ethylene will be the major component, and we will introduce in the polymerization chamber a small amount of the alpha olefin monomers, mostly used like butene or hexene or octene. Okay, the even number of the alkenes of the even number of carbons are much cheaper, and why it is cheaper? Because it is easy to synthesize. And so here we have to do that, we have to take the ethylene plus the another monomer, that is butene or hexene or octene, the small amount, and the process it is called the copolymerization. Okay, now due to small number of, now what you will get? You will get the polymerization and like that, and here you will get, this is actually the coming from the that like that. Okay, so this is actually coming from the butene, hexene or octene, the other monomer other than the ethylene. So that is the strategy to synthesize the LLDP. Okay, and you might have seen that in some book or some journal it is written MLLDPE. Okay, this M actually stands for the Metallocene, or in some journals or reviews or book you might have seen the term Metallocene grade LLDP. That means this MLLDP or Metallocene grade LLDP have been synthesized by the Metallocene based catalysts. Okay, like Kaminsky's catalyst. So now it is very clear that what are the strategies. Now let's see how we can do it in our in industry or in lab. Okay, what will be the protocols? Okay, now you will see here what I have to do from the last slide. So we need the ethylene definitely, because that is the main feedstock. Okay, that is the main component to get this polymer. Okay, that is the polyethylene. Now I need the another monomer for the copolymerization. How we'll get it? Okay, either we have to make it, or you have to get it, but how we'll get it? Somebody has to make. How we can make? Okay, so let's try. So we need another catalyst which can do the oligomerization of the ethylene and give the, so it will be a provider of the another monomer, that is the with alpha olefin monomer other than ethylene, and then we can mix it to get the resulted LLDP polymer. Okay, so what will be the strategy? Very easy to understand, but in reality, okay, we have to much more complex, but in reality you will see it's very easy to understand. So here you will see that what you have to do, this is the system A. Okay, so first is that I need a oligomerization catalyst which will give the alpha olefin other than the ethylene. Okay, so something like hexene, butene, and then you will get the oligomers. So where you will get the oligomer of ethylene. Okay, so it's basically you will get the alpha olefins. Okay, now you will have a mixture of the higher or shorter olefins. So we need a purification definitely, and after purification we have to introduce this to the main polymerization chamber, that is the here. So this is the basically the main polymerization, okay, chamber, that is the B. So in the A we are doing the oligomerization and in the B we are doing the polymerization. Okay, so here you will see two steps are parallelly happening, oligomerization and polymerization, and in between there are other steps. Okay, like see, once you make it the alpha olefins, then you have to do purification. That is a challenging, step. Okay, and then you have to transport it, then you have to store it, okay, the alkene monomer, and whenever required you inject, introduce to the olefin polymerization chamber. So here is basically two-step method. First, why two-step? Because this is the step A and this is the step B, two chambers. So this is one way, one strategy, you can say strategy 1 to make your desired LLDP. Okay, so like from here, if I take this one as a green, that is the main polyethylene, and if I take this one is a blue, that is the monomer other than ethylene, then you will get like this one, and this is basically the LLDP. Okay, very simple. Now what will be the other strategy? That strategy is the not using two steps, single step, and the concept of the tandem catalysis. Tandem means the in situ, okay, the same catalyst will do the two process together. So using the concept of the tandem catalyst, we can make, this is more challenging, but it is a more economic and more easiest method. So what we are doing, we are basically taking the ethylene, that is the monomer, main monomer, and we have to take a catalysis system okay, in situ, not the separate, okay. Then it will make the alpha olefin, one catalyst. That catalyst may be two different molecules or maybe one molecules, homometallic or bimetallic, whatever. So then after getting the alpha olefin and you have the monomer in the system, that is the ethylene, and in presence of copolymerization catalyst 2, you will get the LLDPE. Okay, so the first strategy, that is here, there are two steps. One is the A and the B, that is the oligomerization and the polymerization, but that is two separate chambers. And in this one, strategy 2, we can write here strategy 2, and this one is basically strategy 1. So here you will see that it will be in situ and there will be two catalysts, okay, and one catalyst will do the oligomerization and one catalyst will do the polymerization, and you will get your LLDPE. So that is very advanced and concept, and however it is more simpler, okay, if it is implicated in industries, okay. In some cases it is successful. I will give the real examples. So now we understand that we need two monomers. One is the ethylene, that is the main monomer for polyethylene, and one we need the other alpha olefin monomers like butene, hexene, or like octene or pentene, okay, whatever. But we will be interested which will be more cheaper. Industry will be more interested to make the economic polyethylene with the same properties, okay, so that it is easily accessible to the common people. So here you will see that hexene cost, this is the indicative price, okay, don't take it as the absolute price, this is just an indicative to have a comparison. So here you will see that this is hexene is like for per 500 ml it is almost 4,200, octene is 2,400, decene is almost similar, that is with, you will see that is the C6, okay, C8, okay, so C10 like that. And here you will see that when it is a odd number, the price is quite high, okay. So that's why normally in alpha copolymerization, to make the LLDPE, we normally use the hexene or butene or octene, okay, the even number of carbon atoms, okay. So this is now we will try to understand, okay, how this hexene octene can be made by a very very effective and very famous and very well known process, that is called the SWAP process, okay. So what is the SWAP? That is the cell higher olefin process. So basically we will be increasing the number of carbons to make the olefin, okay, from the ethylene. So it's nothing but a oligomerization, okay. So we will now try to understand what is the cell higher olefin process, what are the steps associated with this one, okay. These are not actually a single step process. Industry follows 3 steps, okay, and this is not a single catalyst or single step, multiple steps, very complex, quite complex, but it is very effective, okay. You will at the end of our discussion, you will understand that how effective it is, how economic it is, and why industries love this process, okay. You will get the byproduct, but that byproduct is also useful for other purpose, okay. So let's try to understand very carefully, because this one is very important, okay. So here again the feedstock is ethylene. So ethylene is the main monomer and main component for the cell higher olefin process. And why we are required? Because this SWAP process actually will give the monomers other than the ethylene for alpha. So it will give the alpha olefin Okay, and why it is needed? Because we have to do alpha olefin copolymerization. Okay, and to make the final product LLDPE. Okay, so let's try to understand the steps. So first step definitely is the oligomerization. Okay, so for ethylene you will get a number of the alpha olefins. So you will get number of alpha olefins. So it's a homogeneously catalyzed ethylene growth reaction. So you will get number of alpha olefin polymers. Generally the nickel hydrogen catalyst, we will discuss the catalytic system. First let's try to understand the strategy. So it's basically the nickel hydride catalysts which are homogeneous in nature, and then what happens, it undergoes the selective oligomerations to even number of carbons, okay, to have the alpha olefin, different type of alpha olefins, like say let's say butene you will get, hexene you will get, octene you will get, different mixtures. Okay, and we have to separate. I will discuss that how we have to do it. Then second step is a olefin metathesis reactions. We have to do what? Why? The isomerations of the higher or heavier fractions. Okay, you will see that in here you will get this like different type of alkenes varying the number of carbon atoms. Like here you will see that quite C20, C10 to 18, okay, which will be much longer, okay, for our LLDP, which are not required. We have to remove from the system, otherwise we will get a good number of branching, okay, and then we will not get the good LLDP if we target for only LLDP. So this one we have to remove. Okay, fine. Now there will be second step is a isomerization of heavier fraction to internal olefins. So what we will get, our result is this one. Now you have to isomerize and you will get basically like this one. Okay, that is for the, and so heavier fractions will undergo the isomerization to have a internal olefins. Internal olefin means that the alkene bond is not at the terminal. Okay, then the recombination, okay, the second step, recombination of lighter and heavier fraction to a mixture of internal olefins. Okay, so this is the step over heterogeneous olefin metathesis catalyst. Okay, so we will be using a heterogeneous catalyst system which actually gives this step, that is the recombination of lighter and heavier fractions to have to get the internal olefins, and then you will get the basically eventually you will get the linear formation of linear internal olefins, that with C10 to C18, okay, carbon atoms. Fine. So C10 to C18 carbon atoms you will get a, so basically you will get a mixture of the internal olefins. Fine. Now third step, because we have to remove this one, or we should not waste this one, because if we waste this, then it will be, the process will not be economic. So what we have to do, converting to a useful material, useful compound, and how we will do it, through hydroformylation and the reduction, and you will get the olefin to aldehyde to alcohol. I will discuss in the next slide that why these are so important. Okay, so let's see. Okay, now these are the steps. That first step is the oligomerization, second step the olefin metathesis, and third step is the hydroformylation and reduction. Okay, let's try to understand now in more depth. So this is the oligomerization. Okay, here you will see this is ethylene, and as I told that this nickel hydride catalyst we will use. I'll come later where you will be what catalyst, what is the chemical structure of the catalyst generally used by industries and which are more common and famous. So what you will get? You will get basically this kind of, okay, alkenes. Okay, so that is the alpha olefins you will get. Okay. Now, like now you have to separate by fractional distillation if there is, if the difference between the in the carbon number of carbon atoms, the boiling point difference will be quite good. So you can separate by fractional distillation to some extent. Okay, like C20 you can separate, but in some cases where the number of carbon atoms are very close, it is very difficult. Okay, so these are the statistical distribution, okay, of the products. So like here you see that lower number of carbon atoms of olefins you will get like 41%, the C10 to 18 you will get around 40%, and C20 you will get around 18%. Okay, and it is important to understand that relative rate, okay, of the oligomerization, okay, is the ethylene is much higher, okay, then the propene, and then the N-butene, okay, and N-pentene, and that is actually good. Otherwise, we'll have a very more amount of higher alkenes. Okay, so this is relative rate of oligomerization. Okay, so this is important, and actually this is more advantageous. Fine. Now, so you are now we got the different alpha olefins. Now second step, that is the olefin metathesis. Okay, so what we are doing here, there will be isomerization of two step here again, the isomerization of alpha olefins to the internal olefins of different carbon atoms, more like so here you will get that C4 to C8 or C20 alkenes with heavier, lighter and the heavier undergoes the isomerization. Okay, so mixture of short and long internal, so this is you will get the isomerization, and what you will get basically mixture of short and long internal olefin. Okay, and you will then it will undergo the metathesis reactions, the alkene metathesis reaction. So we have discussed briefly about the what is the alkene metathesis in the previous classes. So it's basically, you can understand that you can, if you can just break it here, and then it is basically now threading. Okay, so this break it, and then this will be combined with this one, this will be combined with this one, so this will be combined with this one, like that. Okay, and then you will get a mixture of the alkenes, you will get it. Okay, and these are, you will see that this is the if we take a general, so this is like a different combinations of C1 to C3 and C7 to like C14, like that. So what we are doing, we are basically making a medium the internal alkenes with a medium number of the carbons from the lower number and the higher number of carbon atoms. Okay, so this one then after, so this is the range, okay, of, and then the last steps are the, so after that olefin metathesis by heterogeneous catalyst, the last step is the hydroformylation and the reduction. So what you will see, we all know that process, the cobalt catalyzed hydroformylations. Okay, we also discussed very briefly in our previous classes. So here you will see that you will get the aldehyde, okay, and if you reduce it, you will get the alcohol. Okay, so here you will see that total C10, 11, 12. So C12 alkenes here, see here, so C13 alkenes here. So this is one representative example, and from C13 alkenes you are getting the corresponding the alcohol. Okay, so this alcohol actually with the long alkyl groups, it can act as a plasticizers. Okay, so you can regard as fatty alcohols. You see that how this is a longer alkyl groups, and also this is also precursor of detergent. Okay, so here you will see what basically we are getting from the whole process, the SWAP process. We are from the ethylene, this is the final product of what we are getting. We are getting the valuable alpha olefin. Okay, and what we are getting? We are getting the primary alcohol, which are also useful for different applications. Okay, like as a plasticizers, like a fatty alcohols, or it can be used as a precursor of detergents. So you see that there is no waste. Okay, even the byproducts are also used for other purpose, and the industry people love it. Okay, if the whole process economic minimum waste. Okay, so that's why this SWAP process is very much famous and very much effective to make the alpha olefins from the ethylene, and where the byproducts are also useful. So in this class what we learned? We learned the strategy for LLDPE industrial synthesis, how the industry follow the synthesis of LLDPE, the strategy. Okay, we learned that the ethylene oligomerization is very important, because from there we will get the alpha olefins like butene, hexene, octene, and this is actually important for the alpha olefin oligomerization, alpha olefin polymerization, which is eventually will give your the LLDPE, alpha olefin copolymerization. Okay, of ethylene plus another alpha olefin. Okay, and obviously we understand the SWAP process involving various steps. Okay, so thank you, and we will continue in the next class about the we'll try to understand that what are the design and the chemical structure of the catalysts used for SWAP process. That is the first step, the oligomerization process, mainly nickel catalyst, and we will try to understand the mechanism, the bond breaking, bond making process in the next class. Thank you. See you in the next class.